This is 12.2.6 electron microscopes. You need to know about two types of electron microscopes for your A level. These are the transmission electron microscope, which is usually referred to as a TEM, and a scanning tunneling microscope, which is referred to as an STM. Both of these offer much greater resolutions than a light microscope, because a light microscope is limited by the diffraction limit of visible light. Let's start with the transmission electron microscope. Now, as the name suggests, it's got the word transmission, which means the electrons must transmit, must pass through the material in this microscope. So we'll first sketch what this looks like, and then we'll label the process. So this here is an electron gun. This is our anode. These are magnetic condenser lenses. This is our sample, which must be thin. Then we can have a few more magnetic lenses. Called the projector lenses. And then have a screen at the bottom. So the electron gun emits electrons in all directions, and then the electrons are accelerated by the anode's E field. The anode E field accelerates electrons. So electrons make their way out like so. Now, electrons are charged particles, So they are affected by magnets. The magnetic condenser lenses basically behaves similarly to how a lens would when you've got a light microscope, and it causes the rays of electrons to focus on the sample. So magnetic lenses focus the electrons. The electrons are then focused onto the sample. The sample has to be thin to allow transmission of electrons, otherwise the sample could absorb the electrons and nothing passes through. If nothing passes through, you can't form an image using those electrons. So sample must be thin to allow transmission of electrons. Now, some electrons are going to be absorbed. It's inevitable. But not all electrons are. So that will produce light and dark spots in the image. Now, after it passes through the sample, the projector lenses are used to make the electron strike the screen on a larger area, thus making a large image formed from something very, very small. Now, this gives us better resolution than a light microscope. Because lambda is equal to h over square root of 2 MeV. So by increasing the voltage of the anode, we can get smaller wavelengths of the electrons. And these wavelengths will be even smaller than the wavelength of visible light. So we're limited when we use visible light by the diffraction limit, which is limited by the wavelength. Using a thicker sample might slow some electrons down, however. So if you have a thicker sample, it will slow electrons down. That will make lambda then increase and give you poorer resolution than using a thinner sample. So using thicker samples can slow electrons down. Causing lambda to increase. and yielding a lower resolution than if a thinner sample had been used. Okay, let's start a new page. We'll look at the STM next. So STM uses a quantum phenomena called tunneling. So electrons within some energy well have a probability that they can pass through or cross over some kind of gap or a barrier. So they exhibit wave-like behavior. Usually though, most electrons do not cross these gaps because we don't expect them to, so they have a low probability of doing so. So let's write this down. Electrons have some probability of crossing an insulating gap or barrier due to wave behavior. And in quantum mechanics, we'd call this the wave function. So let's see how this would look like in an electron microscope. So this is the surface of a sample. We connect this to power supply. Which is attached to a tungsten tip. And then electrons can tunnel across from the sample to the tungsten tip. So some electrons will tunnel across that gap. Attached to this tungsten tip are devices called piezoelectric transducers. And they do two things. Is they apply some voltage to move the tip around. So they can move it in a plane, for example, to scan it around. That's what's called a scanning tunneling microscope. So the tungsten tip can scan around the sample using the piezoelectric transducers. And the potential differences in currents in there can be measured to know where that tip has been moving. And the movement of that tip can then be used to generate an image along with the current in the tip due to the tunneling of the electrons. So these are piezoelectric transducers, and they move the tip up or down in the XY plane. So here, the electrons tunnel across the gap, as de Broglie waves. And then finally, you need to know the two modes of operation. For the scanning tunneling microscope. So mode 1, the tip does not change in height and remains at a constant height. So if it remains at a constant height, if we imagine zooming right into a sample, they're not perfectly flat. They have contours in them, little peaks and valleys. So we zoom very, very, very close to a sample. It could look something like this. And the tip will remain at a constant height. But as the tip scans along the sample, the distance between the tip and the sample changes due to the contour of the sample. So in parts where the sample is closer to the tip, it's easier for electrons to tunnel across the gap. In regions where the distance to the tip is larger, it's more difficult for electrons to tunnel across to the tip. So therefore, less electrons, there's a slower probability of electrons tunneling across. So when it's closer, you have a larger current being read due to those electrons tunneling. When it's further away, there's less current due to the electrons tunneling. So that difference in current is used to generate an image where you can see the contours of the image due to that current. So it's translated by a computer. So the STM reads the current as the tip scans across the sample. A larger gap results in less current, and then the current is used to generate image. Second mode of operation the tip is allowed to change heights. So tip follows the contours of the sample to maintain a constant current. So if we had the tip on this side, it might be that close. And if the tip moved over to here, it would move up to maintain a constant distance between the tip and the sample. It can move in 3-axis, but in this case, yeah, it's scanning in the XY plane and then moving up and down in the Z plane, in the Z axis. But that way, the distance between tip and part of the sample remains at constant distance. So the probability of tunneling remains the same. So we maintain a constant current in the ammeter. For the tip to move up and down then, the piezoelectric transducers will have to change in voltage to move it around. And the recording of that voltage will then be used to generate an image instead. So here the height changes as tip scans. And that's caused by the piezoelectric transducers. And this voltage is used to generate image. In both cases, there is a significant disadvantage of using an electron microscope compared to a light microscope. So, if we think of living organisms, we can't use a living organism in an electron microscope because in a TEM, you need to have very thin samples. So you have to slice the organism into thin sheets, which will kill it. With the STM, your sample needs to be dehydrated, so all water removed, and then it has to be coated in gold or some material that is conducting, so usually gold. And that's the end of 12.2.6.